Zena gave me thumbs up, so we're good to go. All right. So we're somewhere in the middle of trying out to see where the Martin type theory principles and rules and derivations come in rock. And we were left off at looking at where the action on paths comes in, and we can use it. So we use it to define that 0 is the right unit for addition. So the unit thinks of this comes from, for the mathematicians it should be obvious, but I'm not sure how much algebra the computer scientists get. So this is like being a group, and the unit is the unit of a group. Okay, that's why I call it the unit, but it just means that n plus 0 equals n. You already knew that. The next thing I wanted to show you was how you can use the empty type, right? Where does the empty type come from? So the empty type is called false, and I can do print false. Okay.
Keep looking at it and make it work.
Like this. I'll just take the first front row seat. Okay. So it's the message that I get here on the right hand side says inductive false colon prop colon equal and then nothing. So this nothing here is probably what you would recognize. It's like I don't have any constructors. This colon equal prop here is something that you do not recognize, and this is saying that it's a type of universe prop. And I want to save the best for last, so the universes we will do in like 20 minutes, hopefully. But this is actually the empty type. This is how it's implemented. And there are tactics where you can use the empty type. So let's have an example. I'll have a definition, and I will call it the ex falso example, because this is what I am showing you. And of course, the automated suggestions come from the other file where I coded it up to prepare. So my autocomplete is much better than yours. Okay. So I have the for all a type, so for every type. I can prove that from false, I can prove anything. So A. Okay, so I'll just, I'm just giving you the ex falso statement, basically. But I can prove it using the ex falso tactic. So proof, and then I introduce A and P, and then I have here in my context, I have a P of type false, and I have to prove something of type A, and I can just use the tactic ex falso, and then I need to prove something in false, and I will just say exact P, and then we're done. So did you see what the ex falso tactic did? So it changed my goal here. So I had to prove something in A, and I said ex falso, and it actually uses the rule we call ex falso, which says, okay, if you want something in A, just give me something in false. And luckily, because I have such an interesting left-hand side of the implication here, I'm giving myself something in false anyway. So it's just, a contradiction, and I'm done. Question?
Why does the ex falso rule work? I don't know how to ask this question, but is there a way to write this without writing just the text ex falso, or is it like a primitive thing in Rock?
So ex falso is just a tactic for this term. So let's print, right? Print ex falso example, and hopefully this will be helpful. So the ex falso is called false rect. So it's the induction principle, or the recursor, like with recursion, whatever, induction principle on the empty type, right? And this is how it's defined. So this is induction, and we call it ex falso on the whiteboard, right? And ex falso is called a tactic that will use this ex false rect and instantiate it with the type A that I wanted. Yes, so the primitive one is false rect, and the ex falso is a tactic. Okay? So there's another tactic that also touches on the empty type, and it's the discriminate thing. So it kind of looks the same, and I just want to mention it while I'm mentioning the empty type. So I'll call it discriminate example because it works. And I will have the same thing as above, right? So I'll just copy this whole thing over, but instead of having here false, I will have 0 equals 1. Okay? And the proof will go similarly. I will do intros A and P, and then I will say discriminate, and it just concludes the thing. Okay? So a discriminate tactic is, it works when you have something in, like, if you have a term of the equality type that is in your context, like here, something that is clearly not true, right? It's basically false. So the discriminate tactic will then apply the ex falso for you, basically, and finish the proof for you. So if I print now discriminate example, hopefully I'll see ex falso somewhere there. There it is. It's false rect and blah blah blah, and it used some sort of a equality induction before, right? So discriminate is like a combination of the J rule. This is int, the J rule, and the ex falso. Yes.
Are there cases where it is hard for discriminate to show that two things are not equal?
Yes.
Okay.
And then it just won't work. Like you have to do it then manually. Yes.
I have a potentially silly question, but I'm kind of confused by the syntax. Like, what is the difference between colon equals and colon in this case? Like, are we defining a thing that is of type for all A, 0 equals implies A? Or, like...
Where is the colon equals? Here?
Like, higher up at the beginning, we were defining things using, like the
Okay, let's go to the very top of the file. Here I had ID1,
right. And
colon A, arrow A, colon equals, and then I gave the term.
Right.
Dot, yes. And then I did ID2, where I did blah 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 equals dot, and then I said proof, did some stuff, and edited with defined. Okay? This here, from line 9 to 12, is, you can call it syntactic sugar, for translating it into an actual term that is in line 3 here. So instead of a dot, so if I cannot just finish with a dot here, I have to give it a term, right? And I can give it a term with either colon equals and then directly type it up, or I can allow Rock to do it for me using these tactics that are predefined to help me actually construct the proof.
So the proof of a definition is just the body of the definition?
Yes.
Okay.
So I'm using a proof because the propositions as types, Curry-Howard correspondence says that the inhabitants of the types are proofs and the types of themselves are kind of statements that we're trying to prove, right?
And so
They're propositions.
So the type of our ex falso example was for all A false plus A. That was like the type of the...
Yes. So the type of it, look, all right. We can do check. We want to check what is the type of ex falso. We do check. Whether you're doing false rect or ex falso. Which one?
Like the ex falso, it's like the ex falso example.
The ex falso example. Okay, so I check ex falso example. Okay, I write a dot. I step through it, and it tells me what the type is. And it says it's for all A type. False implies A. False arrow A.
Okay.
Yes.
Thank you.
Good. And if I want to see what the actual term is, I printed it here, right? So if I, okay, I'll just do this. I will do check and print of X also example in this, like one right after the other. So if I do if I do check X also example, it just gives me the name of the symbol that I defined and its type. If I say print, it is giving me the name of the symbol, what it is defined as, and then colon the type. And this is much less readable if you want to see the type. It is the full term that this whole tactic compiled into. Okay, so this is Rock helping you doing the so this equals here, you can imagine as what would happen if I did the colon equals. And then just copy this term. Okay, so let's do that, right? I will do this. I did copy, okay? And then here, instead of is also example, I will remove this thing. I will do colon equals and I'll paste. And then I'll do the dot. And hopefully it will just compute. And if I print it now, you see it's the same type and the same term. So what I had before was just a shortcut, like basically, another way of using exactly the same term. It just uses the Rock tactics so that it's easier for us as humans to do them. But at the end of the day, the magic happens that this is the term that we're producing. Yes?
I think I'm just trying to tie this back to our J's, because looking at the type of X, the X also example has type for all A, type false implies A,
Yeah.
and the false rect also has the same type.
Yes.
And so our J rule is just...
This is not a J rule here. J rule is for the equality. There are no
Sorry.
equalities here.
Okay.
The X falso rule, you mean?
Yes.
Yes.
Sorry. So the only difference between... Okay, so we're essentially just making a lambda that is the same, that's referring back to the...
Okay, this is
already
the speed expansion, right?
Yeah.
Okay, so what you're trying to say is that I could just say here false rect,
Yeah.
and this will probably, if I type it correctly without the... Something happened? No? I cannot find my... What happened? I cannot find my underscore. Ah, there it is. Jesus, okay. See? It is just false right. I just either expanded it.
Yeah.
Yeah.
Okay.
Another question, yes?
Follow up. I think I'm still confused as to what false implies A means for type.
So you mean,
Like, I don't know how to interpret false implies A. as
yes.
type.
Okay, it means, okay, strictly speaking, it's a type of functions
Right.
from the empty type to to A.
So false is just the empty.
False is the empty type.
Nice.
Yes, okay. Sorry, I started with, we will see the empty type and it's called false in Rock.
Right. Yeah, I
But
wrote
maybe
that
you
down.
were doing something, I'm watching you, I'm watching you. Ha! No worries, yes, false is just the empty type, and this is just the X falso induction principle.
Just wanted to comment, one interpretation of X falso is it's just the empty set. Like if you think as functions as sets, like the set whose domain is the empty set, you always have a function for that, right? It's just the empty function. Yeah, so that's one interpretation of it. Yeah, that's all.
Yes,
False rect is built into Rock,
yes,
like in a prelude,
yes,
and it's an eliminator
yes,
for
the empty type,
bottom.
yes.
Oh.
Good,
Can we print false rect?
yes. There it is. Okay. Next, we have the unit type. The unit type is called true. Blah, 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 blah. Where are my? It has one constructor. I called it a star on my whiteboard. Here it's called I. Okay? I will not do the induction principle, but you can believe it's there. I'm just telling you the correspondence between what we did and where we're here. Okay, the last two things I wanted to do was conversion. So the last two of the easiest things. So the variable conversion, you can also see it, right? So definition, and I will of course call it variable conv because it's the autocomplete and it's nice. So I will give myself the type for all natural numbers, 0 plus n equals n implies n equals n. Okay? Proof. I admit these are quite artificial examples, right? But I want to show you how you can see the variable converter here. So I can do intros n and p. Okay, so now I have a proof that 0 plus n equals n, and I want to give you something of type n equals n. And then I can just say exact p, and we're done. And what Rock did for me was Rock converted the type of this variable p in context to the type n equals n, because this is, so plus was defined with induction on the first argument, so this will judgmentally be equal to n, so Rock will just do this simplification and do n equals n. So, you know, if I just say, I can say simple in p, okay, so it will compute the stuff in p, and then I can say exact p. But this, if I don't do the simple, right, it will just do the variable conversion itself. So variable conversion is a thing that Rock knows about. Fine. We can also see the element conversion thing. So I can make a definition. Blah. Oh, it's going to be a banana. Okay, I'm running out of smart names. So I have for all natural numbers n, 0 plus n equals 0 plus n. Okay, we could, you know, prove this with just reflexivity, but I want to show you that we can also prove not just with reflexivity. I can say, well, actually, yes, we want to prove this with reflexivity. Intros n, and then I can do reflexivity here, but actually, what am I trying to tell you? I wanted to show you the element conversion. So I want to show that who can tell me where this is element conversion? I can't see it now. Okay, I have 0 plus n equals 0 plus n. So if I want to have an element of type, okay. Now I don't know where I wanted to show you okay. Let's see. Not now, what am I doing? Okay. Let's print something. Let's say, now I know what I wanted to say. Okay, I want to check banana. I want to check the type of banana. And the type of banana, okay, I will check the type of banana of 0. And the type of banana of 0 is 0 plus 0 equals 0 plus 0. Okay? And then I want to check whether banana of 0 has the type 0 equals 0. Okay? So here we see that the natural, quote-unquote, natural type for banana is 0 plus 0 equals 0 plus 0. But Rock will also say that banana of 0 is of type 0 equals 0. Right? So it does element conversion for us because it knows that 0 plus 0 is 0. So if I want to check it, it will just say, okay, let's see if I can convert this term I have to the type that you want me to have. And this is just, I can derive the banana of 0 has type 0 equals 0, and this is element conversion. Okay. now we can get to the interesting part. Okay? Two more things I want to talk about. One thing is the promised vector and transport. And the second thing is I want to talk about the existentials, right? I want to talk about the dependent sums. I want to talk about the existential quantifiers. And I will start with the easier one, because if I want to talk about the existential quantifiers, I want to do the universes first. So the easier one will be to show you how I do the vector thing. Now I'm going to cheat a little bit, okay? I'm going to copy paste the code from my other file that gives me opposite completed names. Because I don't want to spend 15 minutes trying to derive this for you. I did it yesterday and it was painful. But just to let you see why transport is something you want, okay, I'm going to copy paste this blob of code. And then we're going to walk through it together. But me putting it everything here is going to be not so fun. Okay. I need this. Right, I know. Okay, so we will start with the inductive definition of a vector. Okay, so I'm defining an inductive type with two constructs. So it's I'm calling it vec. It's parameterized over, it takes a type and a natural number that is dimension, and it gives me a type. Okay. Again, this is the universe, but you can imagine that it just says type here. And I'm defining it by giving it two constructors, the nil, the empty vector, and the cons that takes an element. And then for all natural numbers, we can extend a vector of size n with additional element and get a vector of size, the successor of n. So if you did any functional programming at all, ever, this should not surprise you. Who is surprised by this definition? Nobody. Good. Okay. I didn't lose you in my first definition. Okay. Then I can define what a concatenation is. So it takes basically two vectors and gives you a vector of the combined size, and it's going to concatenate them together. So how do I write this in rock? I introduce vectors u and v, and then of course I'm going to define concatenation inductively. So I do induction on V, and because I define this as an inductive type, it will automatically become equipped with the induction principle. Okay, induction principle being the induction principle will say, okay, to define a function out of this type, I will have to define it on its constructors, and then also the computation rules will have to apply similarly to what we did for all of the others, like natural numbers and propositional equality, the others. Okay, so I say induction, and then if I step in the first goal, it says give me a vector of size 0 plus m, and here I have a vector of size m, so it will just be the u. And again, you see the judgmental equality is just computed away. This completely is what they call the variable conversion. Okay? And then the second goal is here. I have this context, so I have u and v and u of size n and m respectively, and then I have to concatenate them and add a new element. So of course I will give it a cons, right? So this ihv is a vector of size n plus m, and I will concatenate one more element to it, namely this little a. So it's a cons, so the next. So the other constructor that adds another element to the vector of size n plus n, and this is the vector that I'm concatenating it to. Okay? And then we define it, and then to reverse a vector, I will do it similarly, right? So I introduce v. I have to provide a vector of this size. I could just say exact v and be done with it, but that wouldn't be reverting it, right? So don't just blindly do whatever your goal says, because to fill this goal to suffice, I could just say v, but then I would get the identity function. That would not be cool. Question? Question? Yes.
I don't know if this is just a tooling issue, but I don't see what the inductive hypothesis is in my editor when I put my cursor on the induction thing. Is it supposed to show that?
So you're clicking on what and don't see what? I
Oh,
didn't
sorry,
hear that.
up in the concat example, when we're using the inductive
Okay,
hypothesis.
so I'll just go here and then I will say, interpret to point, so I'm at this point.
Yeah,
Are you at
wh-
the same point?
yeah, where is the inductive hypothesis?
It's not there yet, I have to do induction first. Okay, I said induction B. Okay, and induction B is giving me two goals. One for each constructor. Okay, now there's nothing yet, there's no inductive hypothesis. I first do the, the base case, which is the nil. I step to the nil, I give it whatever, goal 1 done. I step to the next one, there's my induction hypothesis.
Ah, okay,
Yes. The induction hypothesis is only visible when we're actually trying to construct the, successor, the cons branch of the induction. Okay, to revert a vector, here we are. We don't want to do the identity function, we actually want to do the revert, so I destruct V. It is similar to induction without the induction hypothesis. So for the nil case, I need a vector of size 0, which is exactly nil, nothing new. And for the successor, the cons case, I have a V and A, and I wanna extend it by 1. So I do exact cons A and B, and
Isn't this just returning your original vector?
it's wrong, right?
Yeah.
Well, you see, I was very well prepared for this lecture. Okay, so it should be cons of, right, I actually need the induction hypothesis, right? Right?
Finding ref is hard, right? I need to append at the end.
Yes, I have to append at the end, right? So how do I append at the end?
You need some append.
You could define a map function.
Also, like, why do we need M? Like the implicit argument.
Oh,
M-net, yeah, we
no,
don't need
it's a
M.
copy-paste issue. Yes, we
okay.
absolutely do not need them. Good. I'm so glad that this is not going well because it makes it a really realistic experience. Now I require help from all of the rock experts who have defined this previously, so I need a pen, right?
Yes.
Okay,
You
what
already have the cat already.
What do I have?
Iterative.
Ah, I have a cat, right. Phew, pretty. So, this will not be exact con blah blah blah, this is obviously wrong. It will be exact, what, concat V and cons, the cons A, well, dimension 1, probably,
0.
A, like this.
It won't work because it wants, it gives it n plus 1 and not successor of n.
Yeah.
So exactly.
Uh-huh.
Or you read conf a 0, little a, and then nil.
Cons A. I'll just listen to the experts here. See?
Maybe we can first try constructing like one element vector that goes at the end, like just doing check. And then once we have that, we can try to construct.
Oh, maybe this is.
You need to reverse V first.
I need to reverse V first? Yeah, I need to reverse V first. No.
Yeah,
Yes.
Yes. Good. So this will be a fixed point, right? Rather than a
Yep.
definition. There you go. I don't even know how to revert a vector. See, you can be a successful researcher without knowing how to write a reverse fraction for the vectors. Okay, I need to revert V. Okay, that's good.
If it's a fixed point, we don't need to do induction.
Yeah, pick one.
Induction, we don't need a fixed point.
Okay. You tell me what I'm doing. You in the blue shirt. You asked me this question yesterday. Tell
I
me
mean,
how to.
I guess we can start again by just like right at the end, we'll have to append the one element vector that just contains little a, right?
Yes.
So we can just maybe start by trying to construct just that. And once we have that, we can.
So I know how to do this. I know that cons will append one, but
Cons should
cons, it depends, cons give it to the front, right? I need it to the back.
Yeah, so we.
Yes. So I can do concat,
Yeah.
okay? And then I can concat, so I need first
You need the induction hypothesis.
the induction hypothesis. That's, see, we're getting somewhere. I need, where am I? Okay, I need the induction hypothesis, which I do have. So I am concatenating the induction hypothesis, right, with the one element thing, right? So the one element thing will be cons of something of size 0 and then A, right? So it will be, how is my con defined? I need the type first, A and 0 and nil, something.
But nil A probably, right? Nil big A.
Cons A, nil A, like this.
No,
No.
no, you were right. A, little A, big
Cons,
A,
big A,
zero.
little a, 0, nil. Yeah, cons A, little a, 0, nil. Like this.
Nil needs the A.
Nil A. Nil needs the A. Okay, I'm not listening to you properly.
It won't work.
Big A.
Big A.
And now we miss, yeah.
That also won't work.
Okay, what's the problem now?
It doesn't realize that n plus 1 is successor n. And I don't know how to do that exactly.
You transport it.
Now, okay, perfect. Now I already need transport. Even better. Okay, so let's see how transport looks. Okay, transport looks like this. Okay, we will do check transport. It will look less scary, slightly. Okay, so transport, remember, it will help me go from some type family B of x to B of y if x equals y, right? So how do I see this? Here, I have, for all A, then I have x, the type family, then I have P of x, and then for all y, and here I have the equality, and then I end up in P of y. Why is this so ugly? Better. Then I have P of y. See? So the arguments are commuted slightly differently from what I had on the whiteboard, so we'll have to figure this out, right? So what I want is to go from vector of size s something to vector of size s something else. N plus 1, right? That. And this one says vector of a n plus 1 to vector of a sn. So I want to have proof that n plus 1 equals sn, right? So let's have that. I want to have here